So we have talked about this least squares regression line. And we said it's kind of more than just a best fit line. There is an actual equation that's used to find the best line to model our data. We are going to talk today about how to decide how good our line is, if it's a good fit or not, if we can look at it and decide if there's any outliers in this data. So there's two main things that we're going to look at. The first one is the coefficient of determination. So it is r squared. Now, for a linear model, what was the r? We've seen r before. What was that? It was lowercase r is the coefficient of, or the correlation coefficient.
Is it correlation linear or something?
The lowercase r is the correlation coefficient. Capital R represents the residuals. So we've talked about residual. If it's linear, then it's really easy to find the coefficient of determination. You just really square that value. So it's really not a complicated calculation. We talked about a residual, if you're looking at your formula sheet, it's just your observed minus your predicted. So it's how far apart is the point on our line versus the point we actually saw. The coefficient of determination squares that, so it really just takes away the negatives. So it's showing us if it's 0, then the line has no explanatory value. It's not helpful at all. If it's 1, then it explains 100% of the variation. So this is used to decide how much variation in the response is explained by our regression line. Okay, the goal is a really good line would explain all the variability. A bad line is not going to explain the difference in the points and what we actually saw. We are not doing much of this by hand. We're pretty much strictly looking at calculators today and using that to make some conclusions. Does everybody have that? That we used last week, we had this oil drilling example. So let's go ahead and enter this in our L1 and our L2. And I am going to tell you, I'm going to reference this a couple times today, so just don't delete it out after I'm done with this example, just leave it in there. Last week when we found the correlation coefficient, what did we do? Correlation coefficient, remember, is a measure of how good our linear model is. So we have to talk about something linear. So if you go into stat calculate, we're talking about linear, so it's number 4, the linear regression. Okay, when you do this, you get your y equals ax plus b. Does anybody not have the r on there? Remember we talked about sometimes we have to turn that on. So is anybody's calculator missing that part? So if you're looking at this, it tells us the r at the bottom, but in the middle it gives us the r squared, which is that new piece we're talking about today. It's found just by actually squaring the r value, but we don't have to even do the calculation. So it's 0.5973. So what that means, I'd like to write a sentence for the interpret part. This is like giving you a percent. So it's saying 59.73% of the variation, and my y, which was the drill time, is explained by the regression line. Okay, a great line would be 100% of the variation. A bad line is, 0%. The line doesn't explain any of it. So 59.73, it's not amazing. More than half, so I guess that's good. But it's just telling us a percent of the variation. These y values vary. Almost 60% of that is explained by the regression line. Okay, so anytime I'm asking you to interpret, you're just writing that sentence. Questions there? Yes, ma'am.
Okay, if you enter your data in like different, I guess.
Mm-hmm.
Like say I accidentally skipped a number, and then
It'll
I put
throw
it in
off
at the end,
everything.
it's gonna put.
As long as, okay.
Cause like I skipped 7.92, and so I put it at the end.
Okay, here's the problem. These are like ordered pairs. So if you just move your 7.92 to the end, it's like changing your order pairs to 160, 7.62, 175, 6.89. So if you move to the end, it has to be the entire order pair that gets moved to the end. Just kind of a visual to explain this a little bit more. Here are like 3 different sets of data and a regression line drawn in. Okay, so the first one, you can see that line is really good. It's a really good fit. It would have an R squared of like 0.9999. It's like 99.99% of the data is explained by that regression line. This one, the points are a little bit spread out. That one, it's still fairly strong. That one's a 94.7%. This one, does that line fit the data very well at all? No. That one, the R squared is only 9.4%. So basically, the more spread out your points are, the less the line explains, the lower your R squared value. Does that make sense to everybody? Yes, ma'am.
Whenever we explain it, do you want us to change it to a percent?
Yeah. Okay. So the second piece I want to talk about is more about the residuals themselves. So we did calculate the residual last week. It's our observed minus our predicted. We can use that for a couple things. We can use it to decide if a linear model is good. So should I use a linear model? We can look at if the variance is constant, and we can use it to check for outliers. So we have found outliers before when we did the box plots, but we had to do a lot of work to get there, right? We had to find the upper and lower fence and look at it that way. This is just another option. So, if we look at this residual plot here. So what this is not the actual points from our data, it's the residual. So it's basically each point you're observed minus your predicted. A good model has the residual plots without any pattern at all. It's all spread out. This is a bad model because there is a pattern to my residuals. So what that means is at the beginning, my observed values were way higher, and then it dropped down lower, and then it went higher again. So essentially, if we're plotting the residuals, so not the actual scatter plot, but the residuals, a good model has no pattern at all. Right? If there's a pattern, then that means a linear model is really not a good option. So let's look at one on our calculator. Oh shoot, I'm going to make you delete out all of your other stuff, aren't I? the one that we have in here. So we already have our data, we've already done the regression line. You need to go to stat plot, so that's your second and your y equals. We need to go into plot 1. I want to set it as a scatter plot, so remember that's the first option. But here's where I want it to change. Normally after this point we just enter through everything and our x is our list 1, our y is our list 2. We want to make a residual plot, so we need to change this. So if you look at y list on your calculator right now, it says L2. We need to change that to residuals. So to get there, you have to go second and then push the stat button on your calculator. So second stat. And it brings up a list of names. And the number 7 there at the bottom of the list, it says resid. So that's the one we want to change it to, so number 7. So your calculator right now, your stat plot 1 is on. It's set to scatter plot. Your x's are set as L1. Your y's are set as residual. So then we can zoom number 9 for zoom stat, and we get our residual plot. Okay, if you're looking at this residual plot, that's very crooked. It's something like this. Okay, so is there an obvious pattern there? No. So would a linear model be good? So with the scatter plot itself, if you're just plotting the raw data, you want it to look like a line. But if we're plotting residuals, we don't want a pattern. So there is no obvious pattern. So a linear model is okay. Yes, ma'am.
So what are like the actual points represented?
So for your y's, what it's doing is it's taking the actual point from your y list and subtracting what it would have been if you put it into your linear equation. So we've got the line of best fit. So for each of these, it's taking what actually happened minus what the line would say would happen, and you're giving the difference between them. So we would expect sometimes our line is an over approximation, sometimes it's an under, so we should have positives and negatives there. But no obvious pattern. We don't want like all of them at the beginning to be really high and then drop down really low. That means it was a bad model overall.
So if it was 100, would they like be on the line?
Yep. All right. Let's do another one. So let's do a different set of data. So we have a 1,000 gram sample of radioactive material. We're going to record the amount remaining every day for a week, and this is our data. I want to decide if this is linear. So let's enter this into our table. So deciding if it's linear, we have some options. We could look at the normal scatter plot and do our kind of, oh, it looks mostly linear or not. Residuals is another way of doing that. So to get our residuals, first thing we have to do, we have to have the calculator find the line of best fit, or the linear regression line, so that it can calculate the residuals. So you first need to go into calculate number 4, the linear regression. Okay, you don't necessarily have to write it down. Your calculator is just going to store that in its memory. So now we can go back into our stat plot. We already turned on, we already set it as a scatter plot with the residuals as our y2, so we don't have to change that. It's already there from the last example, so if we just do zoom number 9. Okay, if you're looking at this residual plot, does it look like a good plot? No. Mine looks kind of like a parabola. It's like starting up here, and it goes down here, and then back up. So this is a bad model. What it means is at the beginning, it was overestimating the values. Then in the middle, it underestimated all of them. And then at the end, it overestimated again. So if there's a pattern in the residuals, it is not linear. Does Does anybody need help getting that on their calculator? So we look at this. This is like the original data, and this is the residual. So if it's a good linear model, your residuals are all nice and spread out. If your plot of the residuals shows the spread increasing or decreasing, that's what's called constant error variance. Basically, we want our linear model to be good the whole time. If your residuals start out really close to 0, and then as time goes on, they get further and further spread out, that means your linear model was really good for your beginning points, but as you go on, the points are getting further away from the line. And so that would be a bad thing, right? It means the linear model is good at the beginning, but not later on, or it could be flipped. So if you see, when you plot your residuals, if you see this V-looking thing, that's the constant error variance problem. So that means it's also not a good model. Basically, if it's becoming more spread out over time, we have a problem. We can also find outliers on our residual. If we look, this is the original data, so we would agree that that's an outlier. What happens when you do your residual plot is you have all of your residuals right here, except you had one outlier, so its residual is going to be really, really big. And so then you see it up there. So when you plot your residuals, if you have a point that's way away from all the others, that would be an outlier. Just like when we saw the box and whiskers, we just plotted that outlier out to the side. So not necessarily teaching you something new, just another way to look at it, just another place to pick up on those outliers. We might talk about an influential observation. So if it's influential, it significantly affects the regression line. All right, so I'll let you write that definition down, and then I'm going to talk about the 3 outliers in this picture. So we can have outliers that really aren't a big deal. Case number 2. This is an outlier. Can we all agree with that from our original data? It's far away from all the others. But would that one be influential? Is it going to really change my linear regression line?
No.
No. If you were drawing the line, it's going to look something like this. So even though that point's an outlier, it's not significantly different than the line. So this is an outlier, but it's not influential. What makes it influential is if it's an outlier that is not going to follow that regular pattern. So if it's way above or way below the line. So these 2 points, those are both outliers, and both of those are influential. Because if you put those in there, it's going to either pull your line up or down. Do you guys see the difference? So that case number 2, that's not a big deal, but 1 and 3, if you had those points, you would probably want to throw those out before you did your linear regression line. Otherwise, they're going to completely change your mind and cause a problem later on. Okay, let's do... All right. This is annoying, but let's go back to this set of data that we already had, and I'm going to throw in another point. Okay, so let's say we have day 8 and 120. Okay, was this one a good linear model to begin with? No. So we have to keep that in mind as well. Our residual plot was already bad because we had that pattern. Can you look at your new residual plot? You need to rerun your regression line though, right? So you need to do stat calculate number 4 to get the new regression line with this new point in here. And then we'll go to our stat plots and plot our residuals. And what do you see? Yeah, your residuals look like this, and then you have 1 point way down here. So is that one an outlier?
Yes.
Yes, it's far away from all the others, not following that pattern. Does that make sense to everybody? Okay. So, I am going to stop here. Your assignment is going to be on page 220. And I am going to give you class time tomorrow to work on this, kind of as a peace offering, because I know last week you had a little more homework than usual in here. So we will have class time tomorrow, so this won't actually be turned in.